So 4.1 is graphing polynomial functions. We'll start with just like a couple definitions about polynomial functions in general. So a monomial can be a number, a variable, or the product of a number and one or more variables. It's just basically like one term. And then a polynomial can be a monomial or a sum of monomials. And a polynomial function is basically just like a polynomial written in function notation. So it's actually creating like the input and output aspect of it. But it's f of x equals a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1 power, and so on until you get to your possible constant. So beyond that, the main things to focus on as far as polynomial functions is there are certain things that make it a polynomial function, and there are certain things that, like, if we break these rules, it's no longer a polynomial function. So the first thing is that exponents have to be whole numbers, and like the set of whole numbers is 0, 1, 2, 3, and so on. It can't be negatives, it can't be decimals or fractions. And then the second thing is all coefficients have to be real numbers. So they don't necessarily have to be whole numbers, but they have to be real numbers, meaning like they can't be the square root of a negative, or they can't have I. And then a sub n is the lead coefficient, so when it's in standard form, and n is the degree. Then a polynomial function is in standard form when its terms are written in descending order of exponents from left to right. So highest exponent over the x down to the lowest. And then when it's in standard form, that first coefficient, that first number, is the lead coefficient. And the n, basically the highest exponent on the x, is going to tell us the degree. So for example 1, we're going to get into if something is a polynomial function or not, and then identifying the degree and its lead coefficient. So for a, it's f of x equals negative 4x to the fifth plus 7x squared minus 2. So determining if it's a polynomial function or not, we just have to see if it kind of like meets this criteria. So are all the exponents whole numbers? Yes, because it's just 5 and 2. Those are both whole numbers. And then are all coefficients real numbers? Yep, we have negative 4 and 7, and then the constant is negative 2. So it meets both of those. So it is a polynomial function. So exponents are whole numbers, lead coefficients are real numbers. So we can say that yes, it's a polynomial function. And then as far as if it's in standard form or if we want to put it in standard form is highest exponent down to lowest. So 5, 2, and then this exponent would be like 0, like x to the 0 power. So it's already in standard form, so now we just have to state the degree and the lead coefficient. So the degree is going to be the highest power on x. So in this case, it's degree 5. And then the lead coefficient is, when it's in standard form, it's that number out in front, the coefficient of that first term. So in this case, it's negative 4. And then for b, g of x equals 0.5x squared plus root 3x to the fourth plus 19. So the first one are all exponents whole numbers. So our exponent is 2, exponent 4, and then exponent just 0. So those are all whole numbers. And then are all the coefficients real numbers. So 0.5 is a real number. It's a decimal, but still a real number. And then root 3 is irrational, but it's also still a real number. The only thing that makes it not a real number is if you're taking the square root of a negative, or if the number itself includes I already, because remember I is just imaginary. So it is a polynomial function. Right now it's not in standard form because we go from an exponent of 2 to an exponent of 4, so we need to rewrite it in standard form. So that'd be g of x equals, and then we need to move this root 3x to the fourth up. And then plus 0.5x squared, and then plus 19. And then for the degree, it's our highest power on x, so this is going to be a degree 4. And then for our lead coefficient, when it's in standard form, our lead coefficient is root 3. So lead coefficient is always when it's in standard form. It's not just the form that you're given. So when we put it in standard form, our lead coefficient was root 3. And then for c, h of x equals negative x cubed minus 4x and the negative 4 minus 3x. So the first criteria is all exponents have to be whole numbers. So whole numbers are 0, 1, 2, 3, like and so on. So negative 4 is not a whole number because it's negative, so you can't have a negative exponent. So this is not going to be a polynomial function. And then we can say because of the negative exponent. And then for D, k of x equals x squared plus 9 to the x power minus 1. So the first criteria, all exponents must be whole numbers. So we have an exponent of x, which is not a whole number. So this is also not a polynomial function because of the variable exponent. And then this next example, I'm just going to add a little one to the bottom of this, so we'll call it e. If I had a function, call it f of x equals the square root of x, this is also not a polynomial function because like the square root of x is the same thing as x to the 1/2 power. So that means if you ever see like the square root of x or whatever variable you have, that isn't a function or it's not a polynomial function because the exponent is not a whole number if my exponent is a variable or if it can be written as a variable. And then for graphs of polynomial functions, first we're just going to talk about like even degree versus odd degree in general, and then we'll get into more specifics. So if you have a graph that has, or any function that has an even degree, so I could say, I don't know, f of x equals like 6x to the 8th plus 2x, say to the 5th plus 9. So my degree is 8 because that's the highest power on x. So if my degree is 8, then my end behavior is going to finish off going the same direction. Or if I have an even degree in general, my end behavior will go in the same direction or finish in the same direction. So this graph is just going to be a sketch. It's obviously not going to be this graph, but anytime you have an end degree, or sorry, anytime you have an even degree, the graph is either both going to finish up or it's both going to finish down. So no matter what, no matter how many bumps and turns there are along the way, if it's an even degree, it'll either both finish up or both finish down. And if it's an odd degree, say like g of x equals 8x cubed, I don't know, plus 6x minus 2. I have an odd degree because x to the 3rd power, that's my highest exponent on x. So this graph is going to finish in different directions. So one side will finish going up and one side will finish going down. You may have like some twists and turns and change of direction along the way, but it will for sure end going in different directions. So key takeaway here, even degree finishes off both going up, both going down, or odd degree, they'll go in different directions. And then for the next piece of notes, we're going to get into like the specifics about not just odd and even degree, but now if you have a positive leading coefficient versus a negative leading coefficient. So basically like if the function is increasing versus decreasing. So I'm going to draw the examples for these and then we'll go in and fill in the actual end behavior. So for a positive leading coefficient with an even degree, we'll just do like the most simple example we can think of. So f of x equals x squared, just like the parent function for a quadratic. and use that parent function to figure out the end behavior for any graph that has these characteristics. So we know the parent function of a quadratic looks something like this. And then how we write end behavior is as x approaches negative infinity. So as x approaches with the arrow negative infinity, f of x approaches, and I'm going to stop there. So every single time that you write end behavior, this is going to be written, and then you kind of fill in the blank as the very last thing. So what this is saying, what as x approaches infinity means, that basically means as the graph is moving towards the left. So as the graph is moving towards the left, what is the height of the graph doing? So because if x is approaching negative infinity, that just means like x is getting smaller and smaller and smaller. And as x gets smaller, the graph is going left. So as this graph goes left, it finishes off going up. So in terms of like up and down, the y values, this is going towards positive infinity, or f of x. So as x approaches negative infinity, f of x approaches positive infinity. And then we also have to talk about what happens as x approaches positive infinity. So as x approaches positive infinity, so basically as the graph is moving towards the right, because now as the x values get larger, they're approaching positive infinity, so like just getting closer and closer to that like infinite number. What is f of x doing? So basically like what is the y coordinate or the height of the graph doing? So like as the graph moves right, it's going up. It finishes up. So as x approaches positive infinity, f of x approaches positive infinity as well. And then if you have an odd degree function that also has a positive leading coefficient, the graph will look a little different because we know it's going to look, or it's going to finish going in different directions. So a good example of this would be f of x equals x cubed. You could even use just f of x equals x, because x to the first power, that's still an odd degree. So f of x equals x looks something like this. So I have an odd degree, x cubed, and it's a positive leading coefficient, so it's going to be increasing overall. So the end behavior for this starts exactly the same way. So it's still going to be as x approaches negative infinity, f of x approaches, and then as x approaches infinity, f of x approaches. So basically this is as the graph moves to the left and as the graph moves to the right. Okay, so we'll kind of just copy down those words. So as x approaches negative infinity, so as the graph moves left, what does the height of the graph do, or what does like the y values do? So as this graph moves left, it finishes off going down. So that means as x approaches negative infinity, f of x also approaches negative infinity because it's going down. The x or the y values are getting smaller and smaller. And then for as the graph moves to the right, or as x approaches positive infinity, f of x also approaches positive infinity. So as the graph moves to the right, or as the x values get larger, the graph finishes going upward. So for the y values, that's positive infinity, that's getting larger and larger. So as x approaches negative infinity, as the graph moves left, it also moves down. So that's f of x equals, or approaches negative infinity. And then as x approaches infinity, so as the graph moves right, it also moves up. So that's the f of x approaches positive infinity. And then for negative leading coefficient of an even degree, so it's similar to like f of x equals x squared, but if I have a negative leading coefficient, I'm going to use my example of f of x equals negative x squared. And that's going to be just the parent function of a quadratic, but just like flipped over the x-axis. And we can use this picture to figure out our end behavior for anything that has a negative leading coefficient, even degree. So our end behavior is going to start the same way. Everything's going to be the same up until this last part. So as x approaches negative infinity, f of x approaches. And then to figure out what f of x approaches, we can just look at the sketch that we used for negative x squared. So as x approaches negative infinity, as the graph moves left, how does it finish off? It finishes off going down, so that means f of x approaches negative infinity, because that's going to be like the y values of the f of x values getting smaller and smaller. And then as f of x approaches positive infinity, so as the graph moves right, how does it finish? It also finishes going down, so f of x is going to approach negative infinity. And then for negative leading coefficient with an odd degree, we'll use f of x equals negative x cubed. So that's just going to be this graph but flipped upside down, so it's decreasing. So I can start my end behavior just by kind of filling in what I know is going to be constant for any end behavior, and then fill in the blanks after if that's helpful too. So as x approaches negative infinity, f of x approaches, and we can stop there and add the next line. As x approaches positive infinity, f of x approaches. So anytime you're doing an end behavior, it's always going to start the same way, and you just have to fill in the blank as far as what f of x is doing for those different like x directions. So as x approaches negative infinity, that means as the graph moves to the left, because the x values are getting smaller and smaller, so as the graph moves to the left, it finishes off going up. So that means that f of x, or the y values, are going towards positive infinity. So as x approaches negative infinity, f of x approaches positive infinity. And then as x approaches infinity, so as the x values get larger as the graph goes to the right, so if we follow this graph to the right, it finishes off going down. So that means that f of x, or the y coordinates, are approaching negative infinity. They're getting smaller and smaller. So as x approaches positive infinity, f of x approaches negative infinity. As the graph moves right, it also moves down. And then for example 2, it says, describe the end behavior of f of x equals negative 0.3 x cubed plus 1.7 x squared minus 4x plus 6. This graph would be like really hard to, or this function would be really hard to graph without Desmos, but like you can determine the end behavior just by identifying like key characteristics about the function itself. So the one thing is whether the lead coefficient is positive or negative. So this is already in standard form because it's highest exponent down to the lowest. So my lead coefficient is negative 0.3. So my lead coefficient is negative. I don't even really care what the lead coefficient is, just whether it's positive or negative. And then my degree is going to be whatever the highest power of x is. So my degree would have to be 3, which is odd. So I only care about if the lead coefficient is positive or negative, and then I only care about if the degree is odd or even. The numbers of them don't actually really matter that much. So if my lead coefficient is negative and my degree is odd, this is going to have the same end behavior as any other function that has a negative lead coefficient and an odd degree. So what I like to do is I like to just kind of, sorry, this should have been a negative x cubed. I like to kind of just sketch the picture that goes along with those characteristics. So negative lead coefficient, the graph is going to be decreasing from left to right, and then odd degree means they're going to be like going in different directions. So I know that my graph is going to look something like that. So decreasing overall and then finishing in different directions. If it was like an even degree and, even degree and a negative lead coefficient, it would just be both decreasing. But it's not, it's odd degree, so it finishes off in different directions, and we can use this to write our end behavior. So end behavior always starts the same way. So as x approaches negative infinity, f of x approaches. And then the second line always starts with as x approaches positive infinity, f of x approaches. So this is just saying as the graph moves left, as the x values get smaller, and as the graph moves right, as the x values get bigger. So if we look at this little sketch, as x approaches negative infinity, so as the x values get smaller or the graph moves to the left, it finishes off going up. So that means that f of x is approaching positive infinity because those f of x values or y values are getting bigger and bigger. So as x approaches negative infinity, f of x approaches positive infinity. And then as x approaches positive infinity, as the graph moves to the right, as the x values get larger, the graph finishes off going downward, so that means f of x is approaching negative infinity. And then you'll look and this like matches up the same end behavior that we figured out up here for a general function that had a negative leading coefficient and odd degree. And then the last example is sketching a graph based on like given parameters. So sketch a graph of the polynomial function f with the following characteristics. So f is increasing when x is greater than -2 and less than 3. And then f is decreasing when x is less than -2 and greater than 3. So we're gonna it's just a sketch. It doesn't have to be super accurate, but the biggest thing is just where it's changing direction. So you don't really need to like scale the y-axis at all because it's not telling us like a max or a min or anything like that. You really just need to scale the x-axis to match up with like where it's changing direction. So sometimes it's helpful to draw yourself kind of like dashed lines at where it's changing direction. So since the graph is increasing between -2 and 3, and then it's decreasing before -2 and increasing after 3, it makes sense to just kind of give yourself some dashed lines at -2 and at 3. And then from there we can sketch this graph. So first thing it says is f is increasing from -2 to +3. So when x is between -2 or greater than -2 and less than 3. It doesn't matter where you start the graph because it doesn't specify, so there's no way to know. All that matters is that it's increasing between those 2 points. So we just need to draw a line that's increasing, so it's going up from left to right. And then f is also decreasing when x is less than -2, so that's like to the left of this little barrier. So that means that when it crosses -2, it needs to start decreasing on this side. And then same thing for when x becomes larger than 3, so when x is greater than 3, it's also decreasing. So when it crosses this little barrier, the graph needs to start decreasing. So you just kind of give yourself those guidelines, like this is x equals -2, this is x equals 3. You can erase those lines at the end, but you don't have to, and they just help you kind of guide where your function's increasing or decreasing. So just one more time, f is increasing when x is greater than -2, so to the right of -2, and less than 3, so to the left of 3. So between -2 and 3, it's increasing, it's going up. It's decreasing when x is less than -2, so it's going down on this side of x equals -2. And then it starts decreasing again after, or when x is greater than 3. So it goes from decreasing to increasing to decreasing again. There's like no more points that we know, or there's nothing else that we know about this graph. We can only draw where it's increasing or decreasing.